Hello students, so today we start entropy and production in the irreversible thermodynamics. So let's start. What is entropy production? As we know, if a system is in equilibrium, the entropy of that system is maximum. Okay, so if there is a system which is not in equilibrium, but that system tries to achieve the equilibrium position, and as we know, for equilibrium position the entropy of the system is maximum. So if a system it tries to achieve the equilibrium position, so it means the entropy of that system is continuously increases in the direction in which the equilibrium is reached. So this increase in entropy when the system approaches the equilibrium state, this is known as entropy production. And we know for the irreversible process, which are the natural processes, spontaneous processes, the entropy of the process is always increasing, as according to the second law of thermodynamics, the entropy of the universe is continuously increases. So as from the second law of thermodynamics, which is related to the entropy of the system, entropy is given by change in heat divided by temperature. This is the expression for entropy. And for irreversible process, ds is always greater than or equals to curly q by curly t. Okay, so this can be written as ds minus curly q divided by t greater than or equals to 0. Okay, so to rearrange this can be written as this is equals to d tau. D tau here, d tau, as if you see this equation and this equation, d tau is what? D tau is either greater than 0 or it is equals to 0. Okay, so this is my first expression. Now let us suppose a system. Let us suppose there is a system which is attached with some surrounding, which is we say reservoir. Okay, so reservoir is present at particular temperature T. Okay, so system is in contact with this reservoir. Okay, so let us suppose some amount of heat curly q, it flows into the system from surroundings. From reservoir, some amount of heat it is transferred from reservoir to the system. It means curly q amount of heat is increased in the system and curly q amount of heat is decreased in the surrounding or reservoir. Okay, so decrease in the heat in the surrounding, it is represented by minus curly q. Okay, minus represent here the heat is going out, plus indicates the heat is coming inside. Okay, so for this system the entropy of the reservoir, that is basically equals to, by the same relation, you can see here, by the same relation, this one, this is curly q amount of heat divided by T, but since reservoir transfers this amount of heat to the system, so negative sign is introduced here. Okay, so if we put this expression into this equation, in this equation second term minus curly q by T, it can be replaced with D as reservoir. So this equation it becomes ds plus ds of the reservoir, this is equals to d tau. So this is the entropy of the system, and this becomes the entropy of the surrounding, or you can say reservoir, and the sum of these entropies, this becomes the entropy of the whole universe. So entropy of the whole universe, it will becomes equals to d tau, and d tau we already know either greater than 0 or this is equals to 0. This is basically known as entropy production. This is known as entropy production of the process. Okay, so next we study the entropy production in three different types of the flows. Number one, we will study the entropy production in heat flow. Entropy production in heat flow. So we study three types of the flows: heat flow, second we study matter flow, third we will study in a particular chemical reaction, in a particular chemical process, you can say. Okay, so we will derive the expressions for entropy production in all these three types of flows. So let's start first from the heat flow. Entropy production in the heat flow. So uh, in every method, whether there is the flow of heat, matter, or in a chemical process, so what we have to study, we have to derive a relation of ds for that irreversible process, change in entropy for that irreversible process. Okay, so after finding the expression, some particular expression for this process, our second step जो होएगा, that is to find the entropy production. Entropy production is represented by sigma. This is equals to 1 upon volume into change in entropy of the irreversible process with respect to time. Okay, so this is the expression for entropy production. And volume can be replaced with area into distance, some particular distance, into change in entropy of the irreversible process with time. So if from the first expression we will find the expression for, in the first step we will find the expression for ds irreversible, and then that expression is put in this expression to find the value of entropy production. Okay, so these are the two steps, step 1 and step 2, which we derive for every flow. Okay, so let us start from the heat flow. So in the heat flow we will consider a system. Let us suppose we have a metal rod. This is a metal rod, and we select any two regions of this metal. Let us suppose the temperature of left region is T1 and temperature of right region is T2. We select any two regions of this metal rod. Okay. Let us suppose curly Q1 amount of heat, it is entered at T1 point, and curly Q2 amount of the heat is released from T2 region. Okay, so each region, it is kept constant for particular temperature. Okay, so you can say each region जो है that is isothermal in nature, that is the temperature of the each region with the time it is kept constant. So we can say if at particular temperature, if at particular time the temperature of the T1 region is T1 and temperature of the second region is T2, then even after some time the temperature of both regions, they remain same, they remain T1 and T2. How this is possible? This is possible when the the amount of heat which is entered through the one region, same amount of heat it is released from the second region, which is very close to the first region. Okay, so when curly q1 it becomes equals to curly q2, basically both are in negative direction because curly q1 amount of heat is added to the system and curly q2 amount of heat is released from the second system. So when these two heats they are equal, suppose some 100 kilojoule amount of heat it is entered at T1 point and 100 kilojoule heat it is released from the second region. Only then the temperature of both the regions they remain constant, they remain same with time. Okay, so now we will study the entropy change for the first region, change in entropy for the first region and change in entropy for the second region. For the first region the change in entropy is given by curly q divided by T. For the first region the temperature is T1, the amount of heat added is curly q1. For the second region again same expression, but for the second region temperature is T2, amount of heat added is curly q2. Okay, so for the overall process net entropy change for the whole process, for the flow of heat from region 1 to region 2, it is given by ds irreversible. This is equals to S1 entropy change plus S2 entropy change. Okay, फर्स्ट रीजन दी इंट्रॉपी है करली Q1 डिवाइडेड बाय T1, सेकंड रीजन दी इंट्रॉपी है करली Q2 डिवाइडेड बाय T2. ओके, curly q1 it can be replaced with minus curly q2 divided by T1 plus curly q2 divided by T2. So take curly q2 as common, this will become this expression. So on further solving taking LCM T1 and T2 this will become T1 minus T2. So this is ds irreversible. Okay, so in this process you can say entropy of the universe ds irreversible, this will be positive only when T1 is greater than T2. When this is T1 is greater than T2, then T1 minus T2 becomes positive. Only then this ds entropy left side जो है this will become positive because we are studying a irreversible process for which the entropy of the universe should be continuously increases. So entropy increase means entropy should be positive. So this indicates T1 temperature should be greater than T2 for the spontaneous process, for the process to occur spontaneously. So from the initial system you can see T1 is the temperature from where heat enters and T2 is the temperature from where heat leaves the system. So always T1 should be greater than T2, and we already know heat always flows from a region of high temperature to the region of the low pressure. The spontaneous flow is always from the high temperature to the low temperature, and this is also proved in by this expression. Okay, so now let us suppose that if the temperature differences they are very small, means T1 is very close to T2, then T1 minus T2, this difference is very small. Let us suppose this difference is represented by dt and T1 is approximately equals to T2, and let us suppose both are equals to T. Very small difference, both are almost same. Okay, so this equation becomes ds irreversible, this is equals to curly q into dt, this is replaced with dt and the lower term it is replaced by t square. So this is the first step that we plates for the heat flow. For the second step, we have to find the entropy production. Okay, so for entropy production, the formula for the entropy production is 1 upon volume into change in entropy of irreversible process with dt, with time. Okay, so now we have to find this expression from this expression. So this is ds irreversible. If I divide this expression with dt and multiply it with dt, left side, right side is taken same, curly q into dt divided by t square. This will become the same expression. So this is taken at left side and dt is taken towards the right side. So this will become curly q divided by dt into dt divided by t square. Put this expression into this to find out the entropy production. So entropy production comes out to be 1 upon dx into curly q divided by dt into dt divided by t square. Okay, so now we will just have to rearrange this expression. Minus, second time minus, minus and minus, this will be positive, negative into negative, positive. So here is positive, I will divide this positive into 2 minus. Minus 1 by a into, this term is taken with a. Okay, next dx to a, dx can be written along with dt divided by dx, and 1 by t is present as such. This is just the rearrangement. Okay, we already know this is equals to, negative sign already is there, this is equals to j, flux, since in the flux there is change in the heat, so this is heat flux. This is the expression for heat flux. When we study the topic of flow, flux and force, in the topic of force we study the flux is equals to this expression. Okay, minus 1 upon area into change in that particular physical quantity with time. This will become the flux of that particular flow. Everything else it remains same, that is 1 by t square into dt divided by dx. So this is the entropy production for the heat flow. This is the entropy production for the heat flow that we have to derive.